All right, what's your first step? Very first thing you do with a non-homogeneous is you look at the which leads to your aux. What's your aux look like?
M squared over M squared.
So m equals plus or minus 2, which leads to yc of,
I. Plus minus 2I.
not 2i, because it's negative 4, so it's all good. Yeah. Oh man, I'll make this much more disgusting than I wanted it to.
Oh, that's okay.
All right, that's since for variation of parameters, everything is built off of this. This is the one you want to kind of triple check, right? Because if this ain't right, everything's going to go to shit later. Oh my god. So, bless you. Especially with your eyes, that'll bring in functions that'll make that so much worse than it needs to be. All right, and then I'm going to assume what to get this thing started? U1. Yeah, Y1. I like it. Now this is the one process I don't mind doing the shortcut for. Since the actual full process, it just will always basically be the same, but there's so much to keep track of, it's a little insane. So this is one place where I'm like, all right, I can go straight to the kind of shortcut way. So I can first figure out what U1 prime is, and what's U1 prime built off of, who remembers? All right, so let's figure out what those things are. What's f of x? Yeah, this is f of x. What is, well, y2 we know is this. And the Wronskian, how do I get the Wronskian?
E to 2x. E to 2x.
Yeah, so then you get negative 2 e to the 0, which is 1. So negative 2 minus 2, negative 4. I like it. So that should be your denominator for these U1 primes and the U2 prime. How are we doing there? Is that all right? I like it. I like it. All right, and now, so just fill in what we know. We know that y2 is e to the negative 2x. F of x is x over e to the 3x. And w is negative 4. Did I miss somebody? Did I leave off a negative? Yes. Okay. So cleaning that up a little bit, I get u1 prime is x e to the negative 5x, 1/4 of that. Yummy. Now that's a decent example of a first level worse integral. It's by parts, one of the better by parts you can handle, right? You can be given. So if I do this, you gotta know your by parts. So obviously, what do you always make? U if there isn't that in there, almost always. Any polynomial piece. So you get u equals x, du equals dx. dv then is the other piece. So v is minus 1/5. All right. We'll keep going. I think for U2, I don't have to do every single step here. So this will be 1/4 in front of uv minus the integral of v du. All right. I mean, are you guys with me here? This is all just a little by parts problem, right? Which lives inside a huge DE problem. So this is where it looks like it's looking a lot like what Travis was talking about. We're going to be plus 1/20 And when you integrate this, what do you get? So we're going to do this all at one time. You e to the negative 5x. Yeah, over negative 5, and then times 4, so you minus 1 over 100, which I believe is what you said. Yeah. Cool. All right, let me stop there for a second.
Oh, times 4.
See, that's its own little problem, right? This is, if you haven't learned this yet, I'm not sure how you made it this far. Math is all about taking a big-ass problem, work this little piece of it, work this little piece of it, work this little piece of it, put it back together. I mean, it's the people that kind of see that naturally are the ones that get through it quick, and the people that don't are the ones that are like, how the shit are you doing all this? U2 would be done the same exact way. What would U2 prime look like? What does mine look like? Sweet. U2 prime will now be y1 f of x over the Wronskian. That's the shortcut, by the way, right? Why is this? Why can I just say this so easily? Let's see if you guys really get this. Yeah, but more specifically, why can't I just go straight to U2 prime without building it off of intermediate Wronskians? Because this is built off of Wronskian 1 over Wronskian 2. It's because it is a second order, so I only have to go up that far. So that's why there's this little shortcut for second order. Third order, you'd have a third, 3 by 3 Wronskian, W1, W2, W3 with W. You'd build each U1, U2, U3 primes. Do you guys kind of see what I'm saying? The process would just grow. Just like any matrix kind of problem just grows in dimension. Here we go. Y1 is e to 2x. F of x is still x over e to 3x over negative 4, so you get negative 1/4 x e to the negative x. And then you do an integral just like we just did. All right. Who's done that by now? I don't know if anybody. So you get u2 equals
X over 4.
Yep. So it'll be 1/4 x
E to the negative x.
e to the negative x.
Plus a quarter e to the negative x.
So it really mimics that if you look at it. That 5 is because of the negative 5. So you got 5 times 5 is 25 times 4. But here's 1. 1 times 1 is 1. So you still got a 4. I mean, you can see the pattern. If you don't know what the hell I just said, just do the integration. All right. And then now, so this is U2. This is U1. I'm basically done. Don't stop there, though. I just got one last step, really. And that's just to go back to this. Go back to what started it all off. Throw those things back in there. So now I get U1, times e to 2x. So all these are just going to go up by 2. So this will be negative 1/20 x e to the negative 3x minus 100th e to negative 3x. And then the same thing here. These are going to go down by 2x. So this will be, where'd it go? Here we go. Plus 1/4 x e to the negative 3x plus 1/4 e to the negative 3x. And then I got some nice like terms. Is that cool? Okay. And why would you still not be done once you put those together? Because this is actually y p. And then you have to just add it to your y c, which I have right there. Yay. Freaking. All right. I do want you to memorize these steps. On the test, if you think you forgot something, you just come up and ask me, and I'll let you know if you're right or if you're off by something. You understand? Okay. A few minutes of class is better than 0. Yeah. Sorry. Get to a point where as a teacher, you just got to vent a little bit. So do now, I think we did, like you said, we did 2A last time, right? Real quick, for the benefit of the people that weren't here, let's go over an example Cauchy-Euler, and then you guys can do the last two on there. Do everybody got what they want from this up here? Okay, so the final answer would be y equals that mess, combined like terms, plus this. My God. Okay, I got some extra strong ink. Should be able to get extra high from it. So for Cauchy-Euler, here, I'm going to just do this just because. So that's the form of Cauchy-Euler homogeneous equation. Obviously, it could be non-homogeneous, and then you could do the variation of parameters that we did. I thought I had one more color to work with. Yeah. So we talked about this last time, but for those of you that weren't here, it makes sense that it's not going to be e to the mx, because now I've got this extra x. So it's all about those extra pieces filling in what's being lost in the derivation. The only way this could be 0 is if all of these end up being like terms. Because then that's the only way they could all cancel each other out. So it's got to be, y has got to be some kind of not a polynomial, but x to some power. Because when you take a first derivative, you lost a power of x, but then that fills it back in. Makes it like terms again. That's 2 powers of x that fill it back in for the second derivative, so forth. So Cauchy-Euler would be x cubed, y to triple prime, so forth. Right? I can just keep going forever. And then it gets a little bit harder to factor at that point. Right? Then you better know synthetic division if you hit one of those. We didn't do this all the way out last time, so I'm going to do it. You can see why it's not as pretty as the E stuff, obviously. Nothing can ever be as pretty as E stuff in calculus. But this gets pretty close. When you throw all this stuff in, you get ax squared plus bx plus cx to the m. So you get m minus 1 x to the m, b m x to the m, plus c x to the m. So you can just kill all your x to the m's. So this is repeating that like e to the mx proof step that showed you where the auxiliary equation came from. And our brains sort of forget that and just go straight to it and forget where the hell it comes from. And then you run into this and you start making some weird ass mistakes. So here I get am squared. All the x to the m's cancel. Is that cool? Plus b minus a m. Is that cool? bm minus am. So b minus am plus c. So that's the general rule. If you have this Cauchy-Euler, this is going to be its auxiliary equation. It's that weird little thing in here that's because of the fact that it's not quite so pretty derivatives. Okay. And then you just solve this. You factor it, hopefully, or quadratic equation it, right? So here, we did 2A last time. Try to do 2B and C. I can't remember how those come out, to be honest. I haven't done them since I made this last semester, so maybe I'll do it right now.